Okay, welcome to the second day of ALGA. And to start the talks this morning, I have the pleasure to introduce Alessio Corti from Imperial College, and he will speak on embedding toric varieties in toric varieties.
Thank you very much. Can you hear me? I'm very happy to be here. This is my first visit into Brazil. So, my talk is roughly divided into two parts. Part 1 and Part 2. So, Part 1, I'm going to try to give some context. And Part 2, then I'm going to zoom into today's story, which is the little thing that we can do today that's better than what we could do a month ago. Let me start by putting up the names of my collaborators here. So these are Tom Coates, Al Kaspczyk, and Thomas Prince. We've been pursuing for a long time a project in mirror symmetry, and I'm going to tell you a little bit about the goals of what we want to do. But first, I tell you a little bit about what is mirror symmetry. By the way, it's okay to interrupt me anytime, okay? I absolutely don't mind. If there's anything I can do to make it clearer, please let me know. There are two sides of mirror symmetry. For me, on one side, I have a Fano manifold, or maybe orbifold of some dimension n. And, you know, that just means that the anti-canonical class, the anti-canonical line bundle, is ample. And on X, I study this object here, function, power series, where the coefficient C sub D so by the way, let me first fix a general point in X. So for me, C sub D then is the volume of the space of morphisms F from P1 to X. I should really say nodal curve of gen 0, but let me be somewhat imprecise here. Maps P1 to X of degree D such that f of 0 equal little x. Okay, so that's the object of study on the Fano side. And so so this is the mirror here. So let me draw two lines. The mirror of a Fano is a LG model. And so that's just a variety y together with a function to A1. And on y, I also want a n-form omega, holomorphic n-form. Y is also n-dimensional. And a cycle gamma, a real dimension n cycle of the integers. And I normalize my volume form so that the integral of omega is 1 on gamma. And on this side, I'm just interested in the period function, pi of t, the integral of 1 over 1 minus ft. Well, I need to put the form omega and integrate on the cycle gamma. And I'm saying that x is mirror to y if g hat x equal pi f. Any questions about this? You're all happy about this, yeah?
What kind of right?
I am being vague about this, any kind. Later, and in my life, y will always be taken to be a torus, C star to the n. Any other questions? I'm looking at you. I want to see happy faces. This is a very down-to-earth definition, okay? You can learn just one thing just from the way I've given this definition. There are people who study mirror symmetry as a equivalence of derived categories. That's not what I do. I want my definition to be as practical as possible. Because my goal here, our goal, the thing we are trying to do is we want a computer directory of Fano LG pairs in low dimensions. Maybe smaller than or equal 5. And So I'm interested in the best possible way to put these things in the computer. What's an appropriate data set? From my point of view, I also came, my background in complex algebraic geometry, I'm interested in Fano manifolds or orbifolds, and I'm interested in using this as a way to classify Fano manifolds. By classifying their mirrors first. And so, like, I want to be able to, maybe, hopefully, it's easier to classify the mirrors. And then coming that way from mirror symmetry, when I do this, then they can also index, contain, the address for the mirror is also the best address for the Fano himself. Sounds crazy, preposterous. Try to study something we don't know, Fanos, by studying something we know less about, mirror symmetry, about which there is no evidence that the mirror should be easier in any way than the Fano. I like it. It's crazy. Okay. So I'm just making a small digression about toric varieties. As part of the title, I don't want to assume that everybody here knows about toric varieties. Okay, so in toric varieties, n is some lattice isomorphic to z to the n. And m is the dual. And for me, the starting point here is always a Fano polytope. So a Fano polytope is a lattice polytope P in n tensor R. So for me, it's always compact. To be a lattice polytope means that the vertices of P are lattice points. It's always convex for me. And I also ask that the origin 0 is strictly in the interior of P. So that's a lattice polytope. And if I'm giving a Fano polytope, then I can form out of it a Fano variety. A toric Fano variety. Let me just say here, I say variety, I'm not saying manifold, okay? The key point about this is that this thing is going to be singular. And so how does this work? So here's your polytope. Well, this is a polygon, but never mind. P. And the origin is strictly in the interior, so I will put a little cross where the origin is. And every time I have a face, f of P, I can form the cone over f. Okay, so that's the cone over f. All right? So this final toric variety here, x sub p, so it's a variety. It's a union of affine varieties. So I'm going to tell you what's an affine cover of xp. And the open sets are indexed by the faces of P. And the affine in question is going to be the spec of, it's a bit of a mouthful, but I take the cone over F, and I take the dual cone. So this thing is in N here. This picture is happening in N, so the dual cone is happening in M. And so I take the integer points in the dual cone, and then I form the algebra over that monoid. Okay. And you know, the polytope is telling you how to glue those things together. Are you happy with this? Yes?
What is the structure of the union of all? What kind of structure?
Oh, no, it's a union of specs. This is an open, it's an affine. Yeah. I'm looking at you. Is it okay? All right. Why did I tell you this? I started out with mirror symmetry, then I told you about toric varieties. Why did I tell you this? Well, given P, mirror symmetry, and I'm telling you this is what we know about mirror symmetry, does this for us, puts the smoothings x of xp. Okay, so these are the finals that are deformations of xp that smooth its singularities. Yeah? And these things are mirror to, that's mirror to certain, well, I'm not going to tell you what this means, but we call them mutable Laurent polynomials f with Newton polytope P. And so for me, yeah, the y here then will be, see, a Laurent polynomial is just a function on the torus. So y indeed is just going to be the torus, C star to the n. spec of C of n. So in my world, the Fano LG pairs of which I want to make a computer directory are indexed. The key thing in the data set to give a Fano LG pair is a polytope. And to just give you some idea of the size of the problem, we work in dimension 4 with a list of reflexive polytopes. That's a cool class of polytopes. And that consists of more than 470 million lattice 4D polytopes. I mean, it takes a long time just to write the database on the hard drive. Okay. And you know, you can think we work with the HPC cluster, and you can sort of think about it. You know, if I have a calculation want to perform on single polytope, it takes 3 minutes to do it. And I have 450 million polytopes. How long is it going to take to do that calculation? These are some of the kind of problems that, in the end, we have to face. Okay, for me, that more or less ends part 1. Okay? That was the context. Any questions about this?
What is the cycle that you used there? You also had the omega and the cycle.
Oh, yes. Well, if you're on the torus, yeah, so y is to start to the end. So omega in coordinates, that's going to be the unique translation invariant measure on the torus. Yeah? And the cycle gamma is just the circle. Each lower n is z, and it has a generator, and that's the cycle norm of x1 equal norm of xn equal 1, for example. And because I said that omega is normalized to have volume 1 against gamma, then I probably divide by 1 over 2 pi I to the n. I mean, there is an important point here. We use polytopes to index Fano LG pairs, but then there is the question as to when two different polytopes give rise to the same pair. And so, for example, in dimension 3, we have something 4,319 reflexive polytopes, and they correspond to only 98 Fano LG pairs. And then even on one polytope, there will be many different Fs that one can do. So there is some detail there as well, okay, that I'm not discussing. But basically, we have to work with all these polytopes. Any other questions? Yeah. What's the difference between the two things? I mean, yeah. I do definitely want the directory. Not only that, but I want it to be, I want the database to be out there and to be queryable in real time. So, you know, I want to ask questions. Give me all the Fanos of this degree. And, you know, real time could mean a few hours or something. Okay, so let me start getting into part 2. And so in part 2, I thought, well, okay, at the end, there will be a little technical result, which is the new thing that we learned how to do in the last few weeks. But then I thought I tell you this story. So I want to learn to do mirror symmetry for this simple surface here. I take the blow-up of P113. P113 is a simple surface, the weighted projective space, and it has a singularity, just one singular point, one orbifold point. It's an orbifold, and which is analytically equivalent to C2 mod mu3 acting with weights 1, 1, okay? So it's an orbifold, and I want to blow it up in 4 points. So I thought you should ask me, why, Alessio, why do you want to do this surface? So in fact, I'm just trying to anticipate what you guys might want me to do, because I'm going to try to set myself up, ourselves, our team, as a service where anybody can come and ask, we want you to give us the mirror of this. And then we look at each other, and then we say, yes, we can do it. Okay? And so you may come to me with this surface. I'm not me necessarily you, okay? Somebody. Also, we did this. This was an experiment we ran. It made sense in the context we were doing, and we had exactly this problem, doing the mirror of this surface. And actually, turns out, it's very non-trivial. Now we understand how to do it. Maybe it seems easy, but it's everything like that. Everything is easy once you understand it. When we first looked at this, it was rather non-trivial. So what are the steps? Step 1, remember, mirror symmetries is about toric degenerations. So find a toric degeneration, xp. And step 2, embed xp in a bigger toric variety and use that to recover x. A new model for x. This is the bit that's about the title of this talk, okay? Embedding a toric variety in a toric variety. Here, F will be a bigger toric variety. And then step 3, also find the Laurent polynomial F. So here's xp. I'm going to do step 1. So P is this polygon. So I'm just going to put these dots are the lattice point. It's supposed to be a lattice polygon. So. And this is where the origin is, so we'll put a cross. I know it looks crazy, but this is a very nice polygon. And it's a fact that the surface X, blow up in 4 points of P1 and 3, degenerates to the surface XP. The toric surface XP, where P is this polygon. I did not choose one of the more complicated polygons that do it. So why don't you ask me, Alessio, how did you find that polygon? You pull it out of your hat. So I went to my collaborator Al Kaspczyk, and I told them the degree of that surface, some of the invariants, the singularities is just one little singularity and has degree, some degree, maybe 13 over 3. And, sorry? Yeah. Well, is it? So that one has Picard number 5, and this one has Picard number 1, 2, 3, 4. 2. Yeah, sure. Yeah. 3, maybe 3. Yeah. And then he just took the computer and went through a huge list of polygons until he found one that looked good. So this was a computer search. So remember that you're supposed to do the cones. And so, you know, it's interesting. XP is a pretty singular surface. Also, if I look at this cone here, I see the singularity a third 1 minus 1. The quotient of C2 by mu 3 actually weights 1 minus 1. And down here, I even see, sorry, I do see it because I have some practice with these things. But here, I see a singularity 1 over 9, 1, 2. Because this little vector here is a ninth of this vector plus twice that vector. So it's pretty singular XP, yeah? Then over here, I do see a third 1, 1. That's the same singularity that X has, and that singularity does not go away. As it turns out, these two singularities could be smoothed away, disappear completely by deforming XP. Okay, so now in the rest of the talk, I'm just going to tell you how you do step 2, okay? And this is where the talk is going to get a tiny bit more technical. And so, you know, just hang on maybe. I mean, if it gets too technical for you, then please hang on to this thing I'm telling you now. Everything is about this picture here. So once you understand how it works, it's about this picture. This is a picture of something that in a moment I will call a scaffolding of P. And so that it consists of these two triangles here. Okay, so this picture here contains both the information of how to embed xp in a toric variety and how to build f, the mirror. Okay? So let me tell you how to build the mirror, get that out of the way. So this is step 3 here. And you know, when I see this picture, that's it for me, okay? That's the origin, so that's x and that's y. So I write 1 plus x plus y. So the point down here is x to the minus 1, y to the minus 3. And then I write 1 plus x plus y cube. Voila. So that's the mirror. I'm telling you that the period of this Laurent polynomial equals that strange g hat function of the block of P1 with 3 and 4 points. Okay. So now I'm going to give you this little bit of theory of how you do step 2. And you know, for those in the know, basically we have discovered a new little chapter of toric geometry. So a strut shape that's just a toric variety for the torus Tm. S. So this is a polygon in N. Okay? There is something that I should have told you, and maybe I'm going to say this as an aside. Here, maybe for now. So recall that we spoke about these polytopes in N, and then we did those cones, yeah? So for every face, we have the cone over the face F. And something that's useful is the thing which we call ray map, or ray homomorphism. And so that's the map rho from Zm to N, such that rho, we look at rho 1 up to rho m. These are the rho of E1 up to rho of EM, the images of the M basis vector, the standard basis vector in Zm. These guys are the vertices of P. Okay, so I take these vectors, rho 1, rho 2, rho 3, and I put them together into that homomorphism. Okay? So strut shape is a toric variety S, which with ray map for S from Zm to M, okay? So here the rho is in N. So when I look at this particular S, I'm switching the rho of M and N. Okay, that's a little bit confusing, but that's what it is that I'm doing. And then a scaffolding for P is a collection D1, DM, sorry, d1 dr of nef divisors on S. And so that satisfies a certain condition. I'll tell you about it in a moment. In order to tell you that condition, I have to tell you a little bit more here. So So in a picture like this, the rays rho I or reflective vertices of P are in correspondence with certain divisors Bi on S. And that's because remember how S was built out of affine spaces. And then if you look at one of these rho i's, then spec of C rho I dual that thing is, it turns out, isomorphic to C star to the n minus 1 times C. And so that's how you see a divisor in there, where this last coordinate is allowed to be 0. So anyway, the rho I corresponds to divisors on S. And then a divisor D you can write as a sum of those guys, sum di bi. So here I'm talking about this S here. So in fact, perhaps I want a ray map in M, and this stuff here. So here I'm talking about a polytope in M then. I'm discussing this particular S. And out of a divisor D on S, I can form a polytope P of D. And that's going to be a polytope in N. And that's just the set of vectors in N tensor R such that for every I equal 1 to R, V rho I, sorry, I'm going from I to M, V rho I plus di is larger than or equal to 0. So this is a polytope in N. So it's a bit of a mouthful, but I did promise I was going to get a little bit technical. But out of divisor on S, I get a polytope, maybe I should call it Q, actually. I get a polytope Q in N, okay? And so a scaffolding is a collection of nef divisors on S such that then out of those guys, I can form these polytopes di. And I'm telling the condition is that the convex Hall of all those polytopes is P. The theorem is that out of one of these things, I can form one of these embeddings. the scaffolding gives me an embedding of xp in some toric variety f. So now you see why I said that everything was contained in this picture here. That's P, the outer polygon. And this is a picture of a scaffolding where this would be like Q1, and this would be like Q2. So what I'm saying is that, and P is the convex hull of Q1 and Q2. And I'm saying that Q1 and Q2 correspond to, there's some toric variety somewhere, S, and two divisors, D1 and D2 on S, such that these are their Q's attached to those divisors, and indeed their convex whole is P. So in the example here, I'll tell you how it all works in the example. So S is P2. Nothing would be simpler than that. So that's P2. And this is the ray map. So these guys are rho naught, rho 1, and rho 2. So rho, the map rho there is this matrix. And the two divisors are D naught equal B naught. So the divisor corresponding to rho naught, if you like, that's x naught equals 0 on P2. And D1 is minus B naught plus B1 plus 3 B2. And if you calculate the Q polytopes using this prescription, these are the Q1 and the Q2 you get out of it. And so F then, the ray map for F turns out to be this thing. It's an identity matrix. And then I just put minus the D's. So that's minus 1, 0, 0. And that's 1, minus 1, minus 3. And that's the ray map to form the ambient space F for that construction. And in there, so you see this identity block. I mean, that there is a standard cone in there in F, which looks exactly like C3. And so it's natural to call those coordinates there x0, x1, and x2. And then xp in that toric variety is given by a simple equation. The equation corresponds to the fact that in this row, I have a relation rho naught plus rho 1 plus rho 2 equal 0. And that tells me how to make the equation of x in these coordinates in this affine piece, and that's x0, x1, x2 equal 1. It's just as simple as that. I just want to give the sense there is a simple machinery that allows you to construct these embeddings. This gives a very nice description of X as a hypersurface in a toric variety. Somebody comes to you and says, I want to make the blow up of 4 points in P113. And then, how do you know that that's a hypersurface in a toric variety? This is the way to find out. I promise you, I chose this example because it's one of those that is really hard to do naively, okay? It really helps to, even such a simple example as this, it helps to have this technology in place to treat it. And then once you know it's a hypersurface toric variety, then you can actually use that, and we know how to calculate the g hat function based on that, and one can actually prove for that particular surface that mirror symmetry works in this way. You know, for me, that's it. I'm more or less on time.